limit continuity and differentiability in 3D. So this is the discussion that we'll proceed on. So limit continuity and differentiability. So we have discussed more or less on the limit and continuity. We'll discuss more in the differentiability context. So that is the idea, and especially in the 3D context. So that will proceed on. So if you see the 3D, okay, so okay, so if we see a 3D, then we have kind of a surface. So if this is the surface and this is x-axis, okay, so this is x-axis and this is y-axis. So this is xy plane. If this is xy plane, then if I have function over x and y, then it will be in the z direction. So that will be vertical. So if xy is independent variable, they are independent variable and they lie down on the xy axis, somewhere on the xy plane, then function over xy would be vertical, means in the z axis. So that is the concept. Now we'll first see that what is meaning of continuous when we talk about uh, a plane. Okay, so like the we described, suppose this is a point here. So this point is a comma b. This point is a comma b. If this point is a comma b, then there is a kind of suppose there is a function exists fxy, then it is continuous in a way that if I proceed from a comma b, okay, certainly there is a point a comma b. From a comma b, if I proceed in x direction, if I proceed in y direction, any direction 360 degree, okay, from that point if I proceed, then there should not be any hole or there should not be any mountain. So that is the idea. So if at any point on the xy plane, any point the fxy is considered as continuous when at fxy there is no discontinuity. There is no discontinuity in a sense. Okay, so okay, so there is no discontinuity in a sense that that at this point just just at we can say at infinitesimal small, from this point there is no ditch or there is no sharp right. If that is the case, if there is no hole or there is no sharp right, if that is the case, then this point is considered as continuous. Okay, if now what I am trying to say, that if I know the value of the function at this point, suppose the value of the function at this point is L, that is the limit. So value at this point is L, FAB is L, that is the limit. Now fxy, okay, so a at ab, the value is fab is L, then xy is variable. Fxy, when xy is going towards ab from all the direction where xy tends to ab, fxy where limit x comma y tends to ab, x comma y is very near to AB. So in around AB point, very near to AB point, if there is a point called XY, then FXY should be equal to FAB, that is L. What we are trying to say? Continuity, limiting, and differentiability is very, very big thing. And the way we keep on reiterating that big things always sit upon the smaller thing. There is always layers. Okay. So if I am talking boldly, then I know that my heart is working nice. I know that my stomach is working nice. My organs are working nice. Okay. So I am based upon those organs and I take it for granted that it should work nice. If it is not the case, then I have to make them strong. Okay. If my eyes are not strong, then how I can be strong? Like in calculus, the basic thing, that is limit, continuity, differentiability, this concept should be very powerful. Then only you can proceed further. Considering that basic things is anyway highly strong inside you. Okay. Now, if I talk about continuity at point A and B, then for any point fxy, where xy is very near to A comma B in all the direction, means xy is limiting to A and B, then fxy should be equal to fab. Fxy should be equal to L, that is the limit value at f. This is the limit concept. Okay. But what it states as far as continuity is concerned? It states that FAB, FXY, the FXY should be directly proportional to XY. This is a very big miss. This is not available in any of the book. Okay. So these concepts are all are we are filing disclosure. So if fxy is directly proportional to xy, then with the change in xy, there is a direct change in fxy seen. So if we are decreasing xy, if it is a comma b and we are approaching towards, if it is a comma b and we are approaching from all the sides toward a comma b, all the sides any point is x comma y. If x comma y is slowly becoming a comma b, then fxy should vary the way xy is varying. So if xy is going towards a comma b, means xy minus a comma b is becoming 0. Then delta x delta y is, if it is very small, then fxy minus fab should be small. If xy minus ab is becoming smaller, then fxy minus fab should also become smaller. This is only possible when fxy is directly proportional to x and y. If it is inversely proportional to x and y, then decreasing value of x and y would increase the fxy. If suppose that fxy equal to 1 by x, then if x is decreasing, okay, if x is decreasing means it is going towards a comma b is 0 0. Suppose it is 0 0. So when x is decreasing in the value, then fxy is increasing. If denominator is decreasing, then numerator by denominator is increasing. See, if fxy is inversely proportional to x and y, these things are not available anywhere. So if fxy, we have seen kind of laureates books in mathematics, and the way they explain, sometime you will catch your head. Yes. So please go through like this. So if it is directly proportional, then fxy is, so it's like a spring. The way it is coming in a compression x, then xy, then fxy will also come in compression. Whereas if it is inversely proportional, if it is inversely proportional, then if fxy is proportional to 1 by x and y, 1 by x, y, then with growing x and y, fxy would decrease. With narrowing x and y, fxy would increase. So suppose that a comma b, this is origin, and if we are reaching towards origin, then x is decreasing, then fxy is increasing. Whereas fxy should meet fab. That is not the case here. Okay, so if fxy is directly proportional to x and y, the change in x and y that is seen, same change, similar change, proportional change is happening in fxy, then it is continuous. Okay, one idea. Second idea is that there should not be mountain. Okay, there should, like one case we have taken, fxy equal to x square by x square plus y square. So if I say y equal to 0, then from the minus x and plus x direction, if we approach origin, then it is always 1. X square by x square is always 1. Whereas from plus y and minus y, if we approach, then it is 0. Whereas at 0, 0, it is 0. You consider this case. fxy equal to x square by x square plus y square. So when we are approaching the origin from x-axis, keeping y as constant, then it is 1, x square by x square, y is 0. And if we are approaching the origin from y direction, keeping x constant, then it is 0, if x is 0. So if I approach this from y direction, then it is 0. From this direction, it is 1. So from both the direction, all the direction, if we approach the origin, since value at origin fab is 0, fxy should tend to become 0 when xy tend to be a and b. But that is not the case. In the x direction, it is always 1. And in the y direction, it is always 0. So y direction is alright. This proves that in x direction, there is z value from this side and this side. When it is above the origin, when it is come to origin, suddenly it is dipped. So from origin, there is a z value of 1 and it propagates 1. From the origin, there is z value of 1 that propagates in minus direction. But they are coming like this, and at the origin, suddenly there. So at origin, there is a mountain. Okay, this is not continuous. So continuous in a way that first that fxy should be directly proportional to xy. Here it is not directly proportional to xy, it is constant. It should not be constant. It should be directly proportional to change in xy. And it is not inversely proportional. It is not constant. So if these are the case, then it should be considered as continuous function. If you are continuous, then there is a high chance that it is differentiable. What is differentiable? If my function is differentiable at any point, then rate of change in dependent variable with respect to change in independent variable is defined. Okay, then it is considered as differentiable. If a function f, okay, x is independent and fx is dependent, that is y, then dy by dx, that is differentiable, is valid when fx plus delta x minus fx by delta x. Rate of change in y with respect to change in x, fx plus delta x minus fx by delta x. If this is definite, if this is definitive, if this is valid rate of change, then this is differentiable at point x, any x. Or fa plus delta x minus fa by delta x. If that is the case at any point a, this is single dimension or on xy plane. Now if I say fxy, then fa at any point a comma b, fa plus delta a, b plus delta b, fa plus delta x, b plus delta y minus fab, and then delta x, delta y, whatever is the net distance. So it is it looks impractical, right? It means f a plus delta x, f a plus delta y minus f a b, then delta x delta y. So we can make it delta x square plus delta y square square. I think it is all right now. So if I want to get the differentiability at any point a b, when there is a 3D, means x y, there are two independent variables, then dfx df by df, then differentiable the equation, it would be something like this: f a plus delta x b plus delta y minus f a b by delta x square plus delta y square square. If this is valid, this is definitive, okay, this is plausible, and this is continuous at point a b, then the function fxy is differentiable at point a comma. But question arises is direct differentiation is not possible. Either we can have differentiation in based upon the two independent components a and b, sorry, x and y. So partial derivative is possible. So fx xy fy xy, partial derivative, the rate of change in fxy along x-axis, rate of change in fxy along y-axis. These two we can calculate. But I want both, I want all together. Then why I can say it is differentiable at x comma y, a comma b or not. At any point a comma b, fxy is differentiable or not if I take the partial differentiation along x-axis and y-axis together. If that is the case, then only I would consider it is differentiable. Can we see three things here? Okay, continuous, it should be continuous, one thing. And now we are talking about differentiability in terms of partial derivative. So partial derivative should be possible. If a function is continuous at a comma b, fxy is continuous at a comma b, and fxy is partially differentiable at a comma b, then we can proceed. But idea is it will be called differentiable when I take the partial derivative, that is fxxy, fyxy together. So they come together only in the tangential surface, that is local linearization. Local linearization in the sense, if I take the single variable, okay, so if I have x-axis and there is a function called y equal to x square, okay, this is x-axis, there is a function called y equal to x square, okay, this is the y equal to x square would do go like this. At any point a, x equal to a, if I calculate the differentiation, then that differentiation is nothing but I can that is nothing but slope at that point. Means I can have equation of line with the differential value. So if I say that dy by dx at any point x equal to a, so if this is the line, if this is the equation of a line, then at any point a, if I have dy by dx, then if I draw a line citing y equal to dy by dx into x, y equal to mx, or or y equal to fa plus m x minus a, because x equal to a we are calculating the things. I mean y minus y0 equal to dy by dx x minus x0. That is the concept. Y minus y0 equal to dy by dx x minus x0, or dfx by dx minus y0 equal to d. I'm sorry. I mean to say fx minus y0 equal to dy by dx x minus x0. If it is a value a at x equal to a we are calculating, then fx minus fa, okay, so, or y equal to fa plus dy by dx x minus a. If it is origin, we are calculating at origin, then y equal to mx, simple, y equal to mx, or y equal to dy by dx x. But if it is at any point a, then y equal to fa plus dy by dx x minus a, in bracket x minus a. That is the equation of the line, or y minus y0 equal to mx minus x0, where at x0 we are calculating, or y minus fa equal to dy by dx x minus a. But anyway, so if this is the line, if this is the x-axis, and y equal to x square at any point a, x equal to a, if I have dy by dx, then it is a slope. Then equation of the slope of the line is y equal to dy by dx, whatever the value we got, into x. If it is point x equal to a, then dy by dx x minus a, or y equal to fa, whatever the y value is coming, plus dy by dx, whatever dy by dx is coming at a, x minus xa. That is the equation of the tangential line. Now if I am at 3D, means I have two independent variables x comma y, then if I have a equation of a 3D surface, if I have equation of 3D surface, okay, so with 3D I mean really 3D. Okay, so this is real 3D. So this is a ball and this is real 3D. Now what I'm trying to say, that if this is a 3D, then at any point, if I'm calculating dy, I have equation now called z equal to fxy, z equal to fxy. Now, where fxy is a function over independent variable x and y. So dz by dx, dz by dy. So dz by dx, if I have this point, then partial derivative along x-axis and partial derivative along y-axis. So two derivative I have to calculate. If I have two derivative, then I have tangential surface. Okay. Here also I have tangential surface. Oops. Here also we have, if this is the point a comma b, then at a comma b, if I have partial derivative dz by dx and partial derivative dz by dy, then z equal to z minus z0 equal to mx minus a plus mn, mn or m1 m2, whatever comes in the mind. So I can say z equal to z minus z0 equal to m x minus a plus n y minus b at any point a dot b, a comma b. So if I am calculating if I am proceeding to calculate the differentiability at point a comma b, then if I have two partial derivative dz by dx and dz by dy, then the equation of the tangential surface or local linearity. Okay, local linearity means if I have point A and B, then if I go close, then it should look like a surface that is nothing but a tangential surface. If there it is not continuous, there is sudden hole or sudden mountain, then suddenly there cannot be any tangential surface. So continuity is required. If it is continuous, then tangential surface equation is z equal to, okay, or fxy or lxy. Suppose the tangential surface equation is lxy. So lxy equal to fab, whatever the value of ab means z0. So lxy equal to fab plus m, that is dz by dx at point A, dz by dx x minus a plus dz by dy at point A, y minus b. So L x comma y, L we had fxy. function over x comma y. Now we have another function L over xy. This is the tangential surface equation equal to f a comma b, whatever the value of z at a comma b. At a comma b, we are calculating the tangential surface. So f a comma b plus dz by dx, that is m, slope, dz by dx at point a, x minus a in bracket, plus dz by dy at point a, b in bracket y minus b. So this is the tangential surface at point a comma b. Now in this tangential surface we have both dz by dx and dz by dy. Okay, now I got the equation of tangential surface where dz by dx and dz by dy both are available. That equation of tangential surface, that is Lxy, is equal to fx at point a comma b, so fab plus dz by dx x minus a plus dz by dy x y minus b, where dz by dx and dz by dy are calculated and xy is replaced with a comma b, a and b, whatever value comes, that is m and n or m1 and m2. The way we said the tangential line equation is y equal to mx, the tangential surface equal to z equal to m1x plus m2y. If it is at point a comma b, then tangential surface equal to fab plus dz by dx m1 x minus a dz by dy plus dz by dy, that is m2 and y minus b. Now I received the tangential surface equation. I have the surface equation, means graph. So this is the graph of the 3D. This is the variable. This is what we are seeing, that is the function over x and y. Now suppose this is the tangential surface. See it closely. Okay, I believe it is very small, but I cannot do anything. Okay, now just see it closely. Now can you see there is a gap here? My finger is moving. There is a gap here. So if ball is placed here, then where it is touching the xy plane, all right, after that it is round and there is a gap. So where it is touching the surface, the ball where it is touching the surface, that is a comma b. So at that point, FAB, that is the surface, that is the graph equation, and LAB, L is tangential surface equation. Both are same, LAB and FAB. They are same at point A and B, but beyond that, the sphere is taking round, whereas tangential surface is keeping flat. So there is a gap. Okay, so if this is a sphere and this is tangential surface, if this is tangential surface and there is a big sphere ball, football, then point where it is touching the a and b, there they are same. After that, ball is taking round shape where the tangential surface is flat, so there is a gap that is growing between the ball and tangential surface. So we can say that they are different beyond a comma b. Now we are approaching to a differentiability. How we can say that a function is differentiable at a comma b. Now I know that it is continuous. We calculated the continuous. Okay, where we have the function and we made the limit x y approaching a comma b. In that case, then it should be directly proportional and it should not be constant and it should be inversely proportional. If that is the case, it should vary. Fxy should vary near AB. Okay, the way xy is varying. If that is the case, it is continuous. We calculated. Now we have partial derivative that is calculated at a comma b in x direction and y direction. We have tangential surface also. Now the sphere is round. Sphere is round and tangential surface is this. So sphere and tangential surface, they meet at point A comma B, where they meet just around it. Okay, when tangential surface is approaching a comma b, then tangential surface, if lxy is there, then lxy where x comma y is limiting to a comma b, then lxy should be equal to f a b. Okay, so there is a point called a comma b. At a comma b, lxy at a comma b. So lxy, the tangential surface equation, when xy is approaching a comma b, then lxy value, when xy is approaching a comma b, then lxy, the value, should also be near to fab, the graph value. So Lxy is the tangential surface equation, Fxy is the surface equation or graph equation. They should be equal at a comma b. If xy is any independent component on xy plane, if it is approaching, limiting toward a and b, then Lxy should be equal to or nearing to Fab. Same thing what we have discussed. If that is the case, then it is considered as differential because Lxy, both partial derivative has been taken into the account. If taking two partial derivative in one go, that is Lxy, and Lxy is limiting function. Okay, Lxy is directly proportional to the xy when it is approaching the point a comma b. Same thing we are repeating continuously. Then it is called differentiable because with the differentiable, the concept, that is partial derivative, altogether we have taken in the tangential surface local linearity. If that local linearity is meeting the limit concept, that xy is near to a comma b, then the tangential surface is also equal to the graph equation f. So lxy is equal to FAB when XY is near to AB. If that is the case, then it is differentiable. That is the idea. Okay, so to have the function continuable, first thing limitable, it is limiting. So limit we have talked that xy is approaching toward a comma b, then we call it is limited. So there the fxy value should be equal to the fab. Then if it is happening like this, then function is called continuous. Now if we want to know the differentiable function rate of change at point A, B in all direction is continuous, it is valid, then we calculate the both differentiability, partial differentiation along x-axis and y-axis, and we calculate tangential surface or local linearity. The tangential surface then and actual graph equation both are not same when it is not at a comma b. But if they approach a comma b point, that limit when xy is near to a comma b, then lxy, that is the tangential surface, should be near to fab. This is only possible when okay, so when lxy is directly proportional to change in the xy, not inversely, not constant, but it is complex in the sense we have lxy and fxy, they each near to each other. So we will come to a term called error. Okay, error. So if I am this is a comma b point and this is equation of the surface or graph, then at a comma b the tangential surface and the graph equation fxy and lxy, they are same. Beyond that the sphere go round and tangential surface is there. If it is like that, then there is an error in between. So if a sphere is growing like this and this is tangential surface, if I draw the distance between them, it is keep on growing. At a comma b it is 0. Otherwise the distance is, that is called error. Okay, so the differentiability equation what we saw now, that f lxy and f lxy and fab, they should be similar when xy is limiting to a comma b, that we'll see in the term of error. Now it is simple. Means if error is fxy minus lxy, the surface equation minus tangential equation, that is the gap between them that is coming when we are leaving point a comma b, that error should tend to 0 when xy is approaching a comma b. If that is the case, then we are near to finding saying that the function is differentiable at a comma. So that will proceed on.